Good morning. This lesson is for my Honors Integrated 1 class, but before I get started, I want to say I hope that everyone is doing all right out there. Now, I don't remember if this is section 14.5 or 15.1. It doesn't matter. I'll title it in the section or in the video title. But what does matter are our goals. We have two goals today. Our first goal is the creation of more exponent rules, and our second goal is to investigate how behavior of exponential equations change based on the sign of the exponent value. In the book, they talked about graphing. I wanted to wait until we've established equations and an understanding of the behavior of exponents before I talked about graphing. I feel that it's a better way to tell that story. So we'll start to see today how graphing relates to this and how it relates to the sign of the exponent. So I'm hoping I can clearly tell a story with regards to that. Well, let's go ahead and jump into our first goal, which is the creation of more exponent rules. I have a list of our current exponent rules, and let's just go over them really quick. A to the m power means that I'm multiplying a, or base a, times itself a total of m times, right? So if this was 3 to the 4th power, I would multiply 3 by itself 4 times. Our second exponent rule that we saw is if I have a to the m power divided by a to the n power, that would become a to the m minus n power. And we use that rule to create the next two rules. Any number to the power 0 is equal to 1, and I need to write something. I need to add something to this real quick. And a cannot equal 0. 0 is the only number that this does not happen to. Every other number, it does. Fraction, decimal, any number. 1 divided by a to the power n is equal to a to the power negative n. So if you have a negative exponent up top, you can bring it down below and change the exponent sign. There was a teacher on campus who explained this rule in what I felt was a very articulate way. If you're negative about where you live, which is in the numerator, you can move to the denominator and now be positive about where you're at. But we saw how these rules were actually created. So hopefully, now that we know that they work, we can use them more confidently. All right, so we're going to create rule 5, and we're going to create rule 6. Now, I'm going to be honest with you here. I'm not properly showing these rules, how the creation of the rules. And the reason why I'm not properly showing it is because I have an equal sign. That means that I have to argue that this side turns into that side, and I have to argue that this side turns into that side. Since this is your first time seeing mathematical arguments, let's just worry about turning the left side into the right side. All right? And the way that I'm going to turn this left side into this right side is I have to use the previous rules that I have created. And so these older rules are going to allow me to create newer rules. All right, so let's go ahead and jump into this one. Now, we're going to start with the left side, 1 over a to the minus m. And all that we're allowed to do is we're allowed to use these. So somewhere in here, I have something that I can do to this. And maybe if I rewrite this a little bit different, you might see what I'm talking about. Now, I should also mention this. We have a very, what I would call Pavlovian behavior when it comes to reading equations. And what that means is we're kind of trained without knowing that we're trained. And so whenever you see any of these rules, you see them from the left to the right, the left to the right. And we do that because that's how we read, right? But equations also work from the right to the left. So I mention that because I have the number 1, which means I can replace it with a to the power 0. So this, using rule 3, by rule 3, we now turn a 1 into a to the power 0. Now let's see if I have anything. Do I have another rule over here? And I actually have, this is actually rule number 2. I have the left side of rule 2, so I can now go to the right side of rule 2. So by rule 2, this now becomes a to the power 0. Now I have a minus m, but that doesn't matter. I still have to put a negative up there, right? So this becomes a to the power 0 minus a minus m. Okay? And because I have 2 negatives, I can simplify that. And I get a to the power 0 plus m, which any number plus 0 becomes itself, so this becomes a to the power m. So if I have a negative exponent in the denominator, it's negative where it lives, I can move it up to the numerator, and I now have a positive exponent. It's positive about where it's at. So that was an argument that turns the left side into the right side. If you wanted to turn the right side into the left side, I'll show you the first step. How would I do this? Well, we have to get creative with how we write this. Alright, so we would go like that, and maybe we would have to get creative with how we write a positive sign. Right? Anyways, let's move on to rule number 6. I want to show that a to the power m divided by b to the power m is equal to parentheses a over b, that whole thing raised to the power m. Alright, so notice that the base numbers are different, but the exponents are the same. This only works when that's true. So if I had 3 to the 4th over 5 to the 4th, then I'll be able to write it as 3 over 5 to the 4th power. So let's go ahead and use our current existing rules to rewrite this in this form. So again, we have to start with the left side. And that's shorthand for width. Alright. Now I'm going to use, let's see here, I can't use rule 2 because the base numbers aren't the same. I don't have a 0 exponent, I don't have negative exponents, so by default I can only use rule 1. And I'm going to use rule 1 twice. By rule 1 twice, I can now say I have a times a times a dot 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 times a times a times a, and this is a total of m times, right? And I can also do that for b. So this becomes b times b times b times dot 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 times b times b times b, and again this is a total of n times. Now what I can do, because these guys are multiplying and they're the same number of numbers multiplying in the numerator as there are in the denominator, I can throw parentheses around them. So I will rewrite with parentheses. And I now get a over b times a over b times a over b times dot 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 a over b times a over b, one more a over b. Now remember, I have this a total of n times. I have the right side of this equation now, which means I can turn it into the left side of the equation. So by rule 1 again, I can rewrite this expanded multiplication as A over B n times. So this is going to be important because I need to know this in order to investigate the behavior of exponential equations based on the sign of the exponent value. So I'm going to go ahead and pause this video and erase what I have written. I'll be back. I'm back. So we're on to goal 2 for this lesson, and what I've done is I've written out the exponent rules that we have. Make sure you have this somewhere in your notes that you can always find. And right now I'd like to accept the following rule. A over b to the negative n power becomes b over a to the positive n power. And what that means is this shows that negative exponents flip numbers, which means, and I'll talk about that in a second, but let me remind you what our goal is. We're going to investigate how behavior of exponential equations change based on the sign of the exponent value. And so I have a negative exponent and I have a positive exponent. So let's go back and answer this question. So this shows that negative exponents flip numbers, which means, let's look at it, let's flip a number. Okay? If I have the number 2 over 3, that's equal to 0.6666, and that just repeats. By the way, this is a small spoon. And it's a small spoon number because it's between 0 and 1. If I flip the number, I get 3 over 2, which is equal to 1.5. This is a large spoon number. So flipping a number changes it from a small spoon to a large spoon, or from a large spoon to a small spoon. And remember, we made that table about multiplication. And if I multiply by large spoon numbers, I get larger numbers. If I multiply by small spoon numbers, I get smaller numbers. All right, I really want to stress this behavior because the next lesson is going to be based on that. And I think that this is a good place to talk about this. So I have one example here. I have an exponential equation because my x value is the exponent. F of x equals 3 times 2 to the power x minus 3. And I like to make a table for the domain, which means I'm just going to plug in the x values 0, 1, 2, 3, 4, 5, and 6. Now, I'm going to do this in my head. I'm sorry, I'm not going to write it out, but you can verify it yourself. And I just want to talk about the values here. So hopefully I can calculate this in my head, x and f of x. All right, so if I plug in a 0, I get a negative 3. So this becomes 3 times 1/2 times itself 3 times. And that means I'm going to get 3 over 8. Oh, I know what that number is. 3/8 is 0.375. Okay. If I plug in a 1, I get a minus 2. And so that becomes 1 over 2 because I have to flip it, right? Because it is a 2 over 1. And I have a negative exponent, so I have to flip it. So this becomes 3 times a fourth, which becomes 3/4. If I plug in a 2, I get a power of negative 1. So this becomes 3 times 1/2. So this becomes 3/2 or 1.5. Let me write this value too. Okay, and then if I plug in a 3, I get an exponent of 0. So this becomes 3 times 0. I'm not 3 times 1. 3 times 1. 3 times 2 to the power 0, which becomes 3 times 1, which gives me 3. Okay. Now, if I plug in a 4, this becomes 4 minus 3. This becomes 1, so this becomes 3 times 2, which gets me to 6. I plug in a 4, I get a 6. If I plug in a 5, I have an exponent of 2. So this becomes 3 times 2 times 2, which becomes 12. And if I plug in a 6, I get 3. Oh, sorry. If I plug in a 6, I get a 3 exponent. So this becomes 3 times 2 times 2 times 2, which is going to get me to 24. I want to point something out. Right here I have negative exponents. Right here I have positive exponents. If I look in the negative directions, the value is getting cut in half. And it's getting cut in half because on this side of 3, I'm dealing with a small spoon number multiplied over and over and over again. So every time I multiply by a small spoon number, I'm going to get a smaller result. On this side of the input of 3, I'm left with a large spoon number. And the behavior is a doubling effect. So these problems, again, the behavior changes based on the sign of the exponent. Right? So wherever we're at with the sign of the exponent, that determines, do I have a small spoon number or do I have a large spoon number? I know this is a really odd way to look at it, but as we start to look at the graphs of these in future lessons, you'll start to see that the value that makes the exponent 0 is going to be the borderline that separates the negative exponent results from the positive exponent results. And when we know where that borderline is, we know what type of numbers we're going to multiply by, and we know a behavior. Now, this problem could have looked like this, which would have switched these. Not switched those. These would still be the same. It would have switched these. The behaviors would have switched. We still would have had the negative exponent and positive exponents in the same place, but we would have a doubling the more negative we got, and we would have a halving the more positive we got. So I hope that this makes sense. It's a little bit of a goofy lesson, I know, but we'll discuss it in class. And by the way, see if you can figure out why this is true using these ideas. I would like to see if anyone could figure that out. So I'm going to go ahead and end the lesson here. Again, I hope everybody's having a good day. I'll see you guys later. Bye-bye.